Alright, so welcome back. I thought we'd start today talking about another French aeronaut. This particular individual is Joseph Louis Gay-Lussac, and he's more or less a contemporary of Jacques Charles. He lives in the late 1700s and lives through the mid-1800s. So he's an aeronaut, which means he was absolutely and unequivocally insane. And he would get in balloons, specifically with his friend Boyles, and they would go up high. So Jacques Charles has his notoriety because he was like one of the first people to fly. Well, Gay-Lussac went way, way high up, like 23,000 feet up, like 4,000 feet higher than Kilimanjaro, like most the height of Everest, like 2/3 or more of the height you are in a plane, without pressurization, without oxygen. Right at the limits of human ability, right? And the reason they went up that high is right here in his hand. They would take these glass jars and they were trying to figure out, is the atmosphere down low the same as it is up higher in the atmosphere? And we didn't know. Are the gases the same composition, etc., etc.? But the thing is, it would be brutally cold at that height. And yeah, I mean, just the amount of guts it takes to get in this balloon and go that high is incredible. And Gay-Lussac, while we're going to talk about his law here, is probably most important for discovering water, was 2 parts hydrogen and 1 part oxygen. Like, this guy was a very real scientist and did so by pushing the absolute boundaries of science at his time. So let me get these out of the way and let's take a quick look at his law. At first glance, Gay-Lussac's law is pretty straightforward. At a constant volume, pressure and temperature are directly proportional. So we saw a directly proportional thing in Charles' law. Well, here we are with Gay-Lussac's, the difference being constant volume versus constant pressure. Okay, so it's a relatively obvious law, but it's only obvious once you've studied gases enough to get there. All right, let's look at what this means for us. Let's look at the implication. If we were to graph a directly proportional relationship, would we get a curvy line or a straight line? So, Gay-Lussac's law is pretty straightforward. If you have a container which doesn't change volume, and you heat it up, the pressure goes up. It's probably the one that makes the most sense to you because you have some experience with it. Although I hope not in this way. Let's look at a very bad idea by going to YouTube and looking for examples of Gay-Lussac's law. So here someone's got a sealed pop can in a fire, which raises the pressure because it's rigid until the container fails in an explosion.
Uh-oh. Oh! Whoa! Oh, Jesus!
And this comes from the YouTube channel Beyond the Press. Here they have an oil fire, like a kitchen fire, and they dropped a can of beans into it, which is going to undergo the same rapid pressure rise until it explodes. But this time it's going to happen in a flammable medium with a lot of extra fuel.
Oh. Check that! Oh no! Hey JP, switch to this!
So yeah, don't actually do that. It's an awful, awful idea. Mathematically, Gay-Lussac's law looks really familiar. It looks almost like Charles' law, except we've replaced the V with a P. And again, I use this version here, but I think most students prefer this version here. They're the same thing, right? They're just cross-multiplied. Now, one more thing about Gay-Lussac that I didn't really think about at the moment I was talking about him. His name's actually on the Eiffel Tower. He's one of the 72 people that the French thought were the most important to recognize when they built it. Like, it's easy to say, well, yeah, but I want to point out how important he was at the time and how pivotal he was in science at that point. So one of the things that I will often do with you is if I'm doing a Gay-Lussac's law, I might hide the fact that the volume's not changing by using the words rigid container. Rigid container just means that delta V is 0 or it's at a constant volume. So it's like a code word. When you see rigid container, you need to think, oh, wait a minute, Mr. Nendick's asking about constant volume. This has to be a Gay-Lussac's law. So ultimately, because you've already done more or less this, I'm not too concerned about this law. So I'm ready to move on pretty straightforward. One last note is we're using it and calling it Gay-Lussac's law, although there's another name for it called Amaton's law. Both are used in science, although this is by far more common, so we're going to stick with GL's law. Also, it's a bit more to say, so generally I'm just going to abbreviate it GL. So at this point of the game, we have three laws: Boyles, Charles, and Gay-Lussac's. And each exist when something isn't changing. Boyles when the temperature's not changing, Charles when the pressure's not changing, Gay-Lussac's when the volume's not changing. But what I see here is three equations and three variables, which means I can solve this equation by just combining these three things together. And this is something that Gay-Lussac actually recognized. So that was his big thing. We call Gay-Lussac's rule the volume part, but in reality he did both things. He was the one, because he already had these people's work to work with, that was able to squeeze everything together. So we're going to call that the combined gas law. And what that means is that the pressure and the temperature and the volume are all changing. There's nothing which is a constant. It's a little logical. And so I'm going to save you doing the math to combine it. In class I would generally show you the derivation, but whatever. Here is the combined gas law. P1 V1 equals P2 V2, both of those over denominators of temperature. And again, because they're proportions, we can write them either way, whichever works for us. Still a really easy equation. There's nothing here to really throw us for a loop. And it makes pretty good sense. It also is a little bigger than the others because, well, that is what we need. Right? We got to account for three variables, but nothing scary here. But I want to come back to this concept for just a second. I said these three things are all combined, right? And that Boyles happens without considering temperatures. Well, if I cover up temperatures, hey, look, it's Boyles' law. Charles happens without pressure. Hey, if I cover up pressure, I've got Charles' law. Gay-Lussac's without volume, hey, look at that. We just wrote Gay-Lussac's law out as that. So it's kind of cool. We've actually, if we really wanted to, could just throw in the same number on both sides and get the right answer. So really, Gay-Lussac's, Charles, and Boyles' law are all just this, broken down into slightly easier to work with things. You could answer every question with the combined law if you'd like. One other detail here really quickly is I have a temperature and a gas laws equation. So what unit does it have to be? When we're dealing with the combined gas law, I also would like to throw in a little loop, which is STP, or standard temperature and pressure. And again, this is another one of these code words. STP is just the name for a very specific temperature and a very specific pressure. 0 C at 1 atmosphere. Now, both of these aren't the most useful units, at least at the moment. So what would this be in Kelvin? Right, because you just add 273. And what would this be in, let's go with torr. So this is, again, just something you should have written down off the side. And on the topic of writing things down, let me grab a new sheet for you. So here we go. And in advance, you're welcome. Your teacher should have posted this as part of the Google Classroom assignment today or tomorrow. But this is a summary, and it will go through all things. So you should have access so you can print it yourself or open it and write it on your own time. But let me walk you through what I've typed out for here. First, we have our four laws across the top, and there are equations written in kind of a linear form. Although if you like the fractional form, by all means, write it in that way. Underneath it, I have what's not changing. So for instance, in Charles' law, the pressure doesn't change. The Gay-Lussac's law, the volume doesn't change, etc., right? So I have what the equation is and how to pick it. The relationship, the combined gas law doesn't really have a relationship because lots of things are changing at once. And then under kind of the bold line, I have a list of all the units to help you pick out what's going on, a reminder what STP conditions are, and what the word rigid container means. So my thought is you should always have these notes with you always whenever you're doing gas law problems for the next few days. And to be clear, your homework tomorrow is going to be just like the one on Friday, where you need to use the gas laws to solve for these. I think I'll probably give you around the neighborhood of 8. Nice. So here we go. As I said, the first thing I like to do is go through the question, read it, and identify all the information that's been given. The pressure in a race car tire is 4.25 atmospheres. Okay, let's see. Atmospheres. Oh, look, that's a pressure, right? At 20 degrees C, pretty sure that's a temperature. When the car begins to go around the track, the temperature of the tires increases pretty markedly, up by 65 degrees centigrade. Let's see, that's pretty clearly a temperature, due to friction. Assume the tire is rigid. What's this word mean again? So I'd like to know the new pressure. All right, now before I go any farther, these two things are together. So let's call them 1s. These two things are together, so let's call them 2. So I've got pressures and temperatures, right? And it's rigid. So whose law do I use to solve this? All right, so here we go. Let's solve this problem. Uh-oh, I've hit a problem here. What is it? Okay, I have an unknown pressure, so that's going to be X. And again, this needs to be in Kelvin now, so will you do that for me really fast? Will you look at that? That looks like a pretty straightforward algebra problem. Let's knock it out really fast. All right, 3 sig figs, and also my final answer here must have 3 sig figs, and we're done. Pretty straightforward, just like we've been doing. I don't know, of all the problems, these should start going a little faster. All right, so let's take a look at a harder problem. All right, let's do the same thing. A sample of air in a syringe exerts a pressure of 1.10 atmospheres. Let's see, that's a pressure. At 20 degrees C, we know that's a temperature. The syringe is placed at this temperature. The pressure is increased to, okay, we know this is a pressure, by pushing the plunger in, making the new volume this. So what was the initial volume here? So right off the bat, I see I have temperatures, pressures, and volumes. So which law do I use? All right, so at the start, the pressure and temperature were this. Now, the volume became this, and I'm asking for the initial volume here. So which one of these two things is going to be V1? Right, because initial means 1 first. So our final volume is here, which means this is our final temperature, which means this is our final pressure. So this is actually where a lot of students get stuck up. They have to do this problem and figure out which are 1s and 2s. That's by far the most common difficulty in the combined gas law. That being said, we do know this is a combined gas law problem, and so we can set it up. Got to put this in Kelvin, right? Okay, so P2 has the same units as P1, so I don't need to do a conversion. The only time I need to do conversions if these things don't have the same units. These units have to match. They do right now. Our volume is good. And again, this has to be in Kelvin. It looks pretty easy. Let's solve it. All right, looking 3, 3, 3, 3, 4, so 3 sig figs here. So our initial value was 0.129. And our volume was in milliliters here. So our volume is in milliliters here. So let's do a quick sanity check. It says the volume was reduced, so the fact that our initial volume is bigger than our final volume is good. And these don't look like radical changes. So yeah, this feels pretty comfortable to me. Great. So these problems don't get much worse than what you've been doing. So let's finish by looking at a quick demonstration of Boyles Law. Here this guy's got a vacuum bell jar, which we would normally look at Rockhurst. And he's got a vacuum pump attached to it. He's going to put some peeps in it, and he's going to pull the atmosphere down. So if he makes the pressure lower, what has to happen to the volume?
A few more on top.
It's
just
like a
for
peep
fun.
family in
It
here.
is. It's I don't know what you call a flock of peeps. Is that
A
maybe?
flock of peeps?
I don't know. I don't know what they're called. Okay, so we got the peeps in there. Let's turn the pump on. Start to remove the air. And again, if you watch the peeps closely, you can see
Oh, they're starting to burst almost.
they're starting to get bigger. They're
Yeah.
starting to crack a little bit.
Right.
And kind of the neat thing here, they're getting really nice and big. That works
they
really
are.
well. Kind of the neat thing here is that the elasticity of the peep is going to let it get bigger and bigger and bigger.
Oh, man.
And at some point, though, they're going to start to get a little bit smaller.
I'm seeing it happening. They're
Because-
At the moment, he's going to open up an air valve, which is going to let air back in, and the pressure is going to rise. So what will happen to the volume of the peeps?
Yeah, so here we go.
Oh.
And of course, the peeps even then get a little deflated, right?
Oh, look at.
As you would if you were put inside that chamber as well.
Wah-wah. Poor peeps.
So
Oh, they're not fluffy anymore.
they're not, because we've sort of ripped all those little air pockets, removed the air, and then the sugary goodness can sort of collapse back
and
down
they're
on
kind
those.
of cold.
They're a little bit cold too.
Yeah.
Yeah.
Huh.
So
So that temperature change is part of the combined gas law, because in reality, even though he's trying to demonstrate Boyles' law, he's actually demonstrating the fact that pressure, temperature, and volume all change. So eventually, we're going to need to come up with a rule that lets us change all those things and incorporates our friend the mole. That's where we're heading in pretty quick time. Here he's got some shaving cream inside an ice cream cone, it looks like. So this should be all you need to get the worksheet done tomorrow. That's all you need to worry about from now until Wednesday. And until then, be gentle to each other. Y buen camino en todo.